So, you probably know Faraday's law, right? This idea that a changing magnetic field can get a current flowing in a wire. But what's actually happening there? Well, it turns out that the current we see is really just a symptom of something much, much deeper. It's a clue that points to a fundamental field of nature, one that gets created in the very fabric of space itself. In this explainer, we're going to pull back the curtain on that field and see what it tells us about how the universe really works. Okay, so here's the mystery we need to solve. You take a loop of wire, you put it in a changing magnetic field, and poof, electrons start moving. That's your induced current. But what's pushing them? I mean, for an electron to start moving, some force has to do work on it. There's no battery here. And the thing is, and this is the absolute key, magnetic fields can't do work on charges. They're great at changing a charge's direction, they can make it go in circles, but they can't speed it up. So if the magnetic field isn't providing the push, what is?
So here's our game plan. First, we're going to hunt down that mysterious force. Then, we'll see how finding it completely reimagines Faraday's law. We'll need to talk about two very different kinds of electric fields. After that, we'll get our hands dirty with a concrete example, the solenoid. And finally, we'll zoom out and see what all this means for empty space itself.
All right, so let's jump right in and try to figure out what's really doing the work on those charges.
Okay, so check out this classic setup. We've got a solenoid and we're changing the current running through it over time. That, of course, creates a changing magnetic field inside it. Now, that changing B field induces a current in this totally separate outer loop of wire. The key is that current means electrons are moving, and that means work has been done on them. But the question is still there. By what?
Well, the answer actually comes from looking at Faraday's law in a whole new light. We usually think of it as just a rule for calculating induced voltage, or EMF, but it's actually describing something way more fundamental, the birth of a brand new kind of field.
First, just a quick refresher on induced EMF, which we write with that epsilon symbol. You can think of it as the total push that a single unit of charge gets as it makes one complete lap around a circuit. It's literally defined as the work done per charge.
And boom, here it is. The invisible force doing all the work is an induced electric field. Now hold on, this is not the same electric field that you get from positive and negative charges. This is a different beast altogether, one that's created by a changing magnetic field. The total push, that EMF, is just what you get when you add up the little push from this E field at every single point all the way around the closed loop. In physics, we call that a line integral.
This is a game changer. It lets us rewrite Faraday's law in a much more powerful and profound way. On the left side, you have that line integral we just talked about. It represents the total effect of the induced E field around a closed path. And on the right, you have what creates it, the rate of change of the magnetic flux. By swapping out EMF for the E field itself, we've upgraded from a simple circuit rule to a fundamental law about how fields interact in space.
Okay, but here's where we have to be a little careful. Calling this an electric field can be tricky because it behaves in a way that's totally different from the electrostatic fields that come from charges. Let's break down exactly what separates them.
This right here tells the whole story. The normal electrostatic field on the left, it comes from static charges, and it's what we call a conservative field. Think of it like gravity on a hill. You can walk up, you can walk down, but if you end up back at your starting point, the net work done on you is zero. Now look at our new induced E field on the right. It's non-conservative. It's not like a hill, it's like a whirlpool or a circular escalator. It pushes you in a loop, and it does work on you the entire way around. That continuous circulating push is what drives the current. And because it's not like a hill, you can't define heights, which is why the idea of electric potential, or voltage, just doesn't apply here.
All right, enough with the abstract ideas. Let's make this real. We're going to apply this new understanding to our old friend, the solenoid.
So here's what we're looking at, a cross-section of that solenoid. We're going to assume the magnetic field inside is changing. Our mission, should we choose to accept it, is to use our new and improved Faraday's law to calculate the strength of this induced electric field at some distance r from the center. We'll do it for points inside the solenoid and for points outside. Okay, so let's start with a path inside the solenoid. When we apply Faraday's law, we see that as we make our circular path bigger, the area we enclose gets bigger. That means we're enclosing more and more of that changing magnetic flux. To keep the equation balanced, the E field itself has to get stronger. What you end up with is this really neat result. The induced E field is zero right at the center, and it grows in strength linearly as you move out toward the edge.
But once you're outside the solenoid, things change. As you make your path bigger out here, you're not enclosing any more changing magnetic flux.
You've already got all of it, so the right side of Faraday's law is now a constant, but the left side, the circumference of our path, is getting bigger. For the equation to still hold true, the E field strength has to get weaker, and it turns out it falls off in proportion to 1 over the distance, or 1 over r.
And check this out. This graph just beautifully sums up everything we just figured out. You can see it right here. As we move away from the center, the field strength ramps up in a straight line, nice and linear, until we hit the edge of the solenoid at radius r. And the moment we step outside, it starts that classic 1 over r decay, getting weaker and weaker the farther away you get. Perfect.
Okay, now we get to what is, for my money, the most mind-blowing part of this whole thing. We've been using wires and loops to see what's going on, but what if they weren't even there? So let's ask the big question. If we just take that physical loop of wire out of our experiment, does that induced electric field that was driving the current just vanish?
And the answer is a huge, emphatic no. This is the most profound takeaway of all. A changing magnetic field creates an induced electric field in empty space, period. It doesn't care if there's a wire there or not. The wire was never the cause, it was just a detector. The electrons in the metal were simply feeling a field that was already there, filling the space around them.
And this image just drives that point home. A changing magnetic field fills the space around it with these swirling, non-conservative electric fields. They form closed loops, just like the current we saw on the wire. Any of these imaginary paths you see here, P1, P2, P3, they all have this field swirling around them. The field is a fundamental property of space itself. All right, so let's boil this all down. Takeaway number 1. A changing magnetic flux doesn't just make a voltage, it creates a real, physical, induced electric field. Number 2. This field is non-conservative. It's swirly, not hilly, and it forms closed loops. And number 3, the big one, this field exists in the vacuum of empty space, all on its own, whether there's any matter there to feel it or not.
And that leaves us with one last, really tantalizing thought. We've just proven that a changing B field creates an E field. Now, nature loves symmetry, right? So if a changing B field creates an E field, what do you think a changing E field might create? The answer to that question is what would finally unite electricity and magnetism and reveal the true nature of light itself.